Today we're going to talk about exponential decay. We've been talking about exponential growth over the past couple days. What do you think might look different about an exponential decay graph? Starts high, goes low. So with growth, we had two options. With growth, we could have the above or the below, but either way, it was starting flat and ending steep. For a decay, we are still going to have two options, the above and the below, but we are going to start steep and take a turn to flatten out. Okay. So lesson 8.2 is going to be very similar to lesson 8.1. We're going to look at graphing, look at some applications. We're going to do all of the problems the same, it's just that the outcome is going to look different. So this is a general exponential decay graph. The specific equation for this one was y is equal to 1/2 to the x.
So if there was y to the negative 1/2x, it would just be on the other side of the x-axis?
Yes. And so just like a negative multiplier for growth gave us a lower half instead of an upper half, a negative multiplier here would give us, again, a lower instead of an upper. So we're going to begin by making an XY chart like we did for growths. -1, 0, 1, 2. What do we say plugging in a negative does? Flips it. So we're going to get 5 times flip it, 3/2, gives 7.5. What do we say plugging in a 0 does? Gives a 1 for that part, so it'll always give us our front multiplier. Plugging in a 1 would give us 5 times the fraction itself, 2/3. So it'd be 10/3 or 3 1/3. And plugging in a 2 does what? And squares the fraction or multiplies it by itself to give 4/9. So we multiply, get 20/9. Or 2 2/9. Fractions or decimals are fine, even if they're repeating decimals, because all we're doing is finding points to put onto the graph, and we're going to approximate them anyway. So feel free to use your calculators to do the arithmetic. I'm not going to take them away from you on the test, so you can feel free to go to decimals if you prefer, or fractions. So -1, 7.5. It's going to be floating somewhere up here above the graph. 0, 5. 1, 3 1/3, and 2, 2 2/9 is just a little bit. We're going to connect those points, and we can see they're shrinking down to flattening. We are still going to have a horizontal asymptote at the x-axis, so don't go beyond that axis line. We're flattening towards the asymptote instead of growing from the asymptote. That's the only difference between a decay and a growth. A growth, as we read across, will get steeper, and the decay will get more flat. Questions? For the next example, let's again make a chart. When we plug in -1, we sit on the last problem. That's going to flip our fraction. So it flips the fraction to 2/3. Multiply that by -8, and I get -16/3, or -5 1/3. Plugging in a 0 gives a front multiplier. So I get -8. Plugging in a 1 gives the fraction itself times the front multiplier. Should be -12, and I can see where this is heading, that I'm definitely not even going to care about what I get when I plug in 2, because it's just going to be too far to plot. So instead of doing a 2, I'm going to do a -2, so that maybe I can have one more point to plot. If I plug in a -2, what is that going to do to the fraction?
Make it one higher. Just gonna flip it and then times.
Flips it and then squares it. So we're going to flip it 2/3, square that 4/9. Multiply that by 8 gives negative 32 over 9, or negative 3 5/9. And again, you can feel free to go to decimals if you prefer to just do your arithmetic on your calculator. That's fine, because we're just getting approximate values to be able to plot onto the graph. So when we plot these then, I'll start with that one, negative 2 and about negative 3.5. And then negative 1, negative 5 1/3. Negative 8 is going to fall off my graph, and I don't even have room to get to the 12. So I'm going to connect those and go to an asymptote. What kind of a graph is this? Is it an exponential decay? It's an exponential growth. As we move across, as we read across the book, it's getting more steep, not more flat. So this is actually a growth graph. So the question is, how can we tell from the equation whether it's going to be a growth or a decay? So what was equation number 1 again?
5 times 2/3 dx.
Okay, so 5 times 2/3 of the x was the equation 1. And that was a decay. But this one is a growth. So what can I look for in the equation that I would be able to tell whether I have a growth or a decay?
Would it be negative sign?
What does the negative in the front do?
Oh, that just, no.
That's an upper or lower half, so it's not the negative in the front, but that is one of the differences. What's another difference? The fraction. What about the fraction? Greater than 1. If your base is larger than 1, you will have a growth graph. And we talked about when we did the growths that the further away it is from 1, the more steep it would become. Okay? If that base is less than 1, so in the last problem it was 2/3, then it will create a decay. And again, the further it is from 1, the more steep it will be. Okay, so as that value then gets smaller and smaller as a fraction, that'll create a steeper graph. So 1 would make a completely flat line, and then as we move further away from 1, we're going to get more steep in our graphs. Okay? This equation has something different that we didn't see in either one of those. What's different about this one? A negative exponent. Do you think this is going to be a decay or a growth? All right, so we don't really know. So let's try it out and see what happens. We need to be careful plugging in values to this because there's already a negative with that x. When I plug in a negative 1, that's going to create a negative 1, which is really positive 1. So I get what? 30. When we plug in 0, we get the front multiplier of 10. When we plug in a positive 1, the equation already has the negative, so it's going to make a negative 1. So 10/3, or 3 1/3. And when we plug in 2, since there's already a negative there, that's going to give us a negative 2 power, which will give us 10/9, or 1 1/9. So as I plot these, I'm not going to worry about plotting 30. Even 10 is kind of questionable, but I'll just throw a point somewhere up high there. And then 1 3 1/3, and 1 and a little bit. So did it turn out to be a decay or a growth? Decay. But the base is 3. And I told you on the last one, if the base was bigger than 1, it should be a growth. So what else happened here? The negative exponent. So there are 2 ways that you can have a decay graph. You can have a decay if your base is less than 1, or if your exponent is negative. What do you think about if both of those things happen?
It's possible.
Then it's going to be a growth. They kind of cancel each other out, like a double negative. Okay. So we can tell from our equation whether we should expect a decay or a growth, and that can then kind of verify what we see in our graphs. So it'd be a good idea when you're doing your problems to kind of look at the equation and determine whether you think it should be a growth or a decay, and then after you've made your chart, make sure that the points are lining up with what you think they should be doing. Questions? This one has some additions and subtractions in it. So that's the first thing we're going to do is take care of those. What does the plus 2 do? Left 2 spots. What's plus 1 do? Up 1. So the first thing we're going to do is shift center 2 spots left and 1 line up. And that creates a new center for our graph. Then when we create our XY chart, we just do so for the stuff we haven't dealt with. So -3 times 1/2 to the x. Is this going to be decay or growth?
Growth.
Why? Fraction less than 1, so it's going to be decay. Is it going to be an upper or a lower? And how can we tell? Lower because the negative. So if we kind of think about what our graph is supposed to look like before we start plotting stuff out, then we'll know when we're done if we have a reasonable answer. So we'll plug in our values. Plugging in a -1 flips that 1/2 to make 2, so I get -6. Plugging in 0 gives a front number. Plugging in 1 would give -1.5. Plugging in 2 would square that half, making it a 1/4, so I get -3/4. Again, feel free to use your calculator for arithmetic if you want. I know I just did those quickly. Okay. Now when we plot these, we plot from the shifted center, not from the original center, but from our shift center. Go back 1, down 6. Over 0, down 3. Over 1, down 1.5. And over 2, down 3/4. So that confirms what we expected. It is decay because it's flattening, and it is a lower half. This question also asks for domain and range. What do you think about domain? All reals. Just like growths, decays will have all reals. We can see that it's pointing straight out to the right, so we're definitely going to get everything that way. To the left, it looks like it's pointing straight down, but it is ever so slightly budging over as it goes. So it will cover the entire x-axis. What about range? Range talks about y's. Range is cut off. Is it going to be greater or less? Less than what? 1. It's a lower half, so it's going to be less than, and then the value it's less than is where it holds its asymptote, which is at 1. Questions? Yes.
For 0, when you plug in the 0, wouldn't that make it 0? I don't know.
1/2 to the 0 power is 1.
Oh, right. Yeah.
And then that multiplies by the -3. Anything to 0 is 1.
Gotcha.
I say carefully. Most things to the 0 power 1. 0 to the 0 is a fun thing, but we're not dealing with that.
I don't really understand the range.
Range is our appropriate y values, and we're limited by that asymptote. So where this line is, it's never going to cross. So I'm never going to have any of the values up there. So that means the only y's that I will get are the y's that are below that line. So y has to be less than 1.
Can it be less than 0?
Less than 0, yes, but I do get stuff between 1 and 0. So we can't just say less than 0 because we do also get stuff between the 1 and 0. It will not cross that asymptote, no. It won't even touch the asymptote. So we don't even include an equal to bar.
It's a straight line.
It's never technically completely horizontal, but it's so close to horizontal that it's pretty much. It's never going to touch the line. It's just going to get really close. So close that it doesn't even matter anymore. but it never technically touches it. It's kind of like when like two little kids are in the backseat of the car on a road trip and they're like, I'm not touching you, but you're so close you're basically touching them and you're definitely annoying them. That's the kind of thing with an asymptote and a graph. Like, it never technically touches it, but it's so close that it pretty much doesn't matter. You're still going to get in trouble. What's the +1 do on the next graph?
Push it to the left.
Left one. Side-to-side shift goes backwards. And then with the -2, what's that do? Down 2. That creates our new center. And we make our chart for then just the stuff that we haven't used yet. So 5 times 1/8 to the x. Is this going to be an upper or lower? Upper. How can you tell? +5 in the front. Is it going to be decay or growth? Decay. How can you tell?
Because 1 is less than
Fraction less than 1, 1/8. Is it going to be steep or more flat? Steep. How can we tell?
Because it's a really small.
The further that number gets from 1, the more steep it will be. So if we're working with a growth, a big number far away from 1 will be more steep. If we're working with a fraction, then the closer we get to 0, so the further away we get from 1, the more steep it's going to be. So it's going to be a really steep one, which means we're going to have trouble plotting a lot of points to this one, but we'll do our best. If I plug in -1, that's going to flip over that 1/8 to make it 8 times 5 is 40. Not plotting that. If I plug in 0, we get the front multiplier of 5. If I plug in 1, I'm going to get 5/8. If I plug in 2, that's going to square that fraction, making it 1/64 times the 5 is 5/64. Basically 0, but not quite. Okay, really, really, really tiny, but not quite 0. So I'm definitely not plotting that first one. From the shifted center, not from the original, but from the shifted center, over 0 up 5. Over 1, up a little bit more than a half. And I can't even plot 5/64 because it's so tiny, so I really only have 2 points to go off of for this one. This graph takes a really sharp turn. The further that base is from 1, the more steep the graph will be. Domain. All reals. Range talks about y, greater or less.
Always greater than -2.
Greater than -2. Greater than because it's an above graph, and -2 because that's the line where it gets cut off.
Wait, when would the range not be all real numbers?
The range? The range is not all real numbers.
The-
The domain? The domain will always be all real numbers for exponential graphs. We looked at an equation very similar to this one when we talked about exponential growth. What is different about this equation?
So 1 minus.
1 minus. In our other one, we had 1 plus r, which gave us a value of bigger than 1, because I would have 1 plus some rate. Gives me a base bigger than 1, which gives me a growth. Here, I'm going to do 1 minus a value, so that base will be smaller than 1, which will give us a decay. You buy a new car for $24,000. The value of the car decreases by 16% each year. First question asks us to write a model. So we're going to use that formula. What is A? 24,000. A means initial value. What is R? Rate of decay, which is 16%, 0.16 as we put it in. Don't put it in as a 16, put it in as a 0.16. To the power of t, for a model, remember you should have both variables still present. A model is a general equation that we can later plug in anything we want. So we get 24,000 times 0.84 to the t. Part A also says, find the value of the car after 2 years. How do we do that? Plug in a 2 for t. So in the calculator, we do 24,000 times 0.84 to the power of 2, and that gives me 16,934. So after owning the car for 2 years, it's close to 17 grand, which means a loss of 7 grand over 2 years. Questions on part A? Yes.
When we were doing like the first lesson, we always did 1 plus the percent. Why did we do that?
1 plus is going to give us a base bigger than 1, so it'll create a growth.
Okay.
A decay will happen when we do 1 minus, because that will make our base less than 1. So growth will add and decay will subtract. Part B wants us to graph this. So like when we did growth, we're not going to care about negatives. We don't care about before we bought the car, and we don't care about negative money. Our equation was 24,000 times 0.84 to the t, and we'll make a chart for that. We already know a couple values. We know 0, 24,000, and we know 2, 16,934. We'll use part C to guide us in picking other numbers. Part C says, after how many years will the car be worth $12,000? So we want to pick some numbers to plug in that will give us an answer of close to 12,000, and we just kind of guess and check. So what do you think? 4? All right, so we'll try plugging in 4. That gives me 11,949. So I'd say that's about the answer to part C, is after about 4 years. Why do you think they picked 12,000? Half of the original value. So in 4 years, you've lost half the value of your car. Financially, buying a new car is a horrible decision. There are some reasons why people may want a new car, like my husband's very picky with the way his cars are taken care of. So if you're the first owner, you know it's been taken care of well. But financially, it's a horrible decision because this is actually pretty accurate. Cars are not good investments. Buy a car a few years old and let that rapid decay have already happened. When we plot these, we'll need to choose an appropriate scale. I think about 2,000 should do it, that we can get all of this in. So I'll count by 2s here, really counting by 2,000s. So then as we plot our points, I plot 0 years, 24. 2 years, right about 17. And 4 years, right about 12. So we can see the beginning of this decay curve happening. We don't know necessarily how the steepness is going to pan out on the other end as it heads down to 0. So if you wanted to, you could grab some more points over there, but you don't have to. 3 points is good enough. Questions? Yes. Last example, there are 40,000 homes in your city. Each year 10% is expected to disconnect from septic and go to sewer. Write an exponential decay model for the number that are still connected to septic. So, our starting equation is A, 1 minus R, because it's decay, to the T. What is A? 40,000. What is R? 0.1 for 10%. And t is t. We're not going to plug anything in yet because in a model we need two variables. Part A still asks us then to do one more thing. Use this model to estimate the number of homes after 5 years. So we'll plug a 5 into this equation. And we get 23,620. Questions on part A? Part B then wants us to graph and use that graph to estimate when we get 17,2. So we'll let that be a guide for us in picking numbers when we make our chart. Now, should we expect this to be a steep graph or a not so steep graph?
Not so steep.
Why not so steep?
Because each year only 10%.
Only 10%. It's not a big rate of change, so that base is 0.9, which is still pretty close to 1. The closer that base is to 1, the more flatlined it's going to be. So we'll start with some values. We know 0, 40,000. And we know 5 was 23,620. So we're asked about 17,2. So what do you want to plug in? 8. 17,219. Good guess. All right. If we don't hit it right on, then we just kind of keep on using some guess and check to get ourselves close to that value. So it looks like 8 years is going to be the answer. And then we want to plot these points for our graph. I'm going to count by 4,000s to fit everything in this time. You get 40,000 on the axis, over 5 up to just below the 24, and over 8, 17. So we're not getting the really sharp turn here, which is what we expected, that we wouldn't see a really sharp turn in this graph. Questions? Okay, so decay is very similar in process to growth. It's just that our output picture looks different because in decay our values are shrinking over time instead of growing over time. So your assignment is from 8.2.